Welcome to our session. We have a whole bunch of exciting content to cover today. So as you're coming in, feel free to grab seats closer to the front. We have plenty of chairs. This is a massive auditorium. My name is Nick Orlove. I'm a BigQuery product manager. I specifically focus on many of the real-time capabilities of BigQuery. So things like the ingestion into BQ, the egress out of BigQuery, and then also the real-time data processing of data within BigQuery. With me will be Pavan Edara, a Google Distinguished Engineer and one of the founding architects of BigQuery. So if you love using BigQuery like I do, he is a big part to thank for that. And then also we're joined by Pinaki Mitra, the Vice President of Data Science at UPS Capital, who's going to be talking about their use cases for continuous analytics and the integration with AI and ML. To start, I wanted to do a quick informal poll of the engineers in the room. So raise your hand if you view your role more along the lines of a data engineer or data analyst, that being you help your company to analyze data, process, ingest, transform, et cetera. Okay, maybe like half or so of the hands raised. Go ahead and put your hands down. Now separately, raise your hand if you view your role as more in the lines of an AI engineer, that being you help your company build, train AI models, or leverage AI for things like inference, anomaly detection, content analysis, stuff like that. It's smaller, maybe 10% or so. Okay. After the session, be sure to meet your peers because from my vantage point, From my vantage point, the worlds of data and AI are really starting to converge. And what that means is that as the pace of innovation becomes more widespread, the speed at which companies will go from raw data to usable AI will increase faster and faster and become increasingly important. And so what this means is that as processes are streamlined, the roles of data and AI engineering are coming more aligned, coming closer together. So where these teams used to be disparate and more separated, the roles are becoming more blurred, and the role of a data engineer and the role of a AI engineer are starting to become cross-pollinated. In fact, I predict that in a few years' time, the successful data engineer will be just as familiar with using an AI model as using SQL. Now, the worlds of data and AI are converging for three main reasons. The first is that in an industry with thousands and thousands of AI models, what really differentiates one AI model from all the other AI models is the data that's used to train it. And so that means that the underlying data, the unique data within your organization, is your differentiator. It's your edge, your secret sauce, if you will. The second is that leveraging AI is becoming easier as it becomes more democratized. So as you've undoubtedly seen throughout this conference, you no longer have to be a PhD-level data scientist in order to build applications with usable AI. And the third is that the integration of AI into both operational and analytical systems means that AI-led decision-making can be handled in more of a real-time and in-band manner. And both data decision makers and data leaders are agreeing with this and seeing the value of integrating AI into their organizations, with 84% of decision makers believing that Gen AI will help organizations access their insights faster, and then 73% of data leaders feeling that real-time access to data is extremely important for their business. Now, the unification of data and AI offers tremendous business opportunities, but the harsh reality is that few companies are actually achieving this. In fact, only 19% of companies actually excel at maximizing value from their data. And the reason that most companies fail to turn data and AI into a true differentiator is because of the approaches and the systems of the past are really not meant for this new AI era. For one reason, data and AI are not being leveraged at scale across organizations. They're being leveraged in silos, disparate, separate systems which are built for specialized purposes and separated and difficult to access for different use cases. And second, where AI models are leveraged, the complexity makes it so that very few people are actually able to take advantage of that. This means that the tooling is due to the tooling being disjointed, complex, expensive, and requires specialized skill sets. Plus, it's traditionally difficult to actually govern. And last but not least, as the world moves towards just-in-time interactions with customers, employees, and applications, the lag in data processing, analyzing, and AI inference causes teams to struggle in making data-driven decisions in a timely manner. In fact, I recently came across a blog that I wanted to share with you all that talks about the minimum latency requirements for both operational and analytical workloads. Now, in the realm of a traditional analytical workload, real-time generally means 15 minutes or less. However, in the world of operational workloads, it requires a whole nother degree of thinking. And that's because in the world of fraud detection, patient monitoring, IoT insights, customer service, real-time isn't minutes, real-time is seconds. And so what this means is that this is a dramatically different problem to solve for. Now, it's a problem because in the traditional world of data warehousing and data platforms, we generally think of real-time as the real-time ingestion of data into our platform. It's about how to get data in as soon as possible. However, the processing, analysis, and actually insights garnered from that data still operates akin to more of a batch process. And that's because while data is streamed into your platform in real time, the current tooling forces users to work with more discrete chunks of data, where you're essentially running the same query again and again and again and again, exactly like a batch process. And of course, ingesting real-time data is very vital for modern data platforms and making data-driven decisions. In fact, BigQuery is in the process, or BigQuery ingests hundreds of petabytes of real-time streaming data every single month. And I've been at Google for 7 years, and I swear, the scale at which we operate still boggles me, still incredible. However, a different strategy is really required to address the challenges of this merging data and AI world in order to make these real-time decisions that are required. So in order to address this requirement, we leverage Google's philosophy of building 10x in order to solve for 10x problems, rather than having an incremental 10% mindset. So solving a 10x problem really means that you have to look at the problem statement itself entirely different. You have to have a completely different approach. So using the mindset of 10x thinking to meet the worlds of the converging data and AI, we thought about how to enable data processing the moment that it arrived. We thought about the native integration required across the entire Google Cloud stack in order to break down data silos and maximize usability. We thought about democratizing this capability and using the language of SQL in order to do so. And lastly, we thought about using BigQuery, which is already at the center of many of our customers' data strategies. And that brings us to BigQuery continuous queries. So this feature is currently in private preview and going into public preview later this summer. BigQuery continuous queries extends new streaming SQL capabilities within BigQuery in the form of SQL jobs that can run indefinitely, processing data the moment that it arrives. It offers deep integration with Vertex AI, PubSub, Bigtable, and partner tooling that's currently under development in order to simplify the process of building more capable event-driven pipelines. So things like dynamic data enrichment and entity extraction, AI-driven real-time anomaly detection, and uniquely personalized content generation of data that's already in your data warehouse. And using this extensible model, BigQuery continuous queries amplifies downstream applications and SaaS services with real-time enterprise knowledge of the data that's already within your platform. This means up-leveling your business to process, analyze, transform, and use AI with your data in real time is now as easy as writing a SQL statement. Now, for those of you asking yourself, so data gets processed faster and there's more integrations across services, that's great and all, but so what? Where's that magic? Now, the so what, and the really exciting part, the magic that happens, is when we think about the broader trend of the converging data and the AI worlds together. Because this feature isn't so much just process your data faster, but it's really the ability to unlock operational capabilities to combine the enterprise knowledge of the data within your data platform with the prediction, extraction, and generation capabilities of AI. And it's during these conversations that I've had with customers where they come to the aha light bulb conclusion, where they start to think about new use cases that they haven't really explored before. So things like building real-time ETL pipelines to transform and use AI to enrich your data as it arrives into BigQuery, or even for things like reverse ETL use cases. Or creating uniquely tailored experiences for your customers based off of how they've already interacted with your business in the past and all the data that's already within BigQuery. Or crafting comprehensive anomaly detection to react in real time to protect your business from threats or fraud. Or developing customized event-driven applications which leverage PubSub to trigger downstream services based off of the custom AI models that are built and running across your data within your environment. And we'll see more of these use cases in demos later on. So stepping back a bit, it's probably worth a little bit of time to talk about why this was built in BigQuery and why that's special for our customers. And at the root of that answer is the BigQuery architecture, which continues to be the foundation of innovation within the BigQuery platform itself. Our unique architecture takes full advantage of the underlying infrastructure that sits underneath some of some of the world's largest applications and online services with Google. It offers separation of compute and storage to bring together our highly available and durable storage service, our scalable and elastic compute service, our high-speed network that connects the two, and our distributed data shuffle tier. But why does that matter for you, our customers? Why should you care? There are three big reasons for that. The first is, this is the primary reason we are the price performance leader in this space. The separation of compute and storage allows us to have more granular scaling and the ability to leverage infrastructure advantages that lead to price efficiencies. The second is that this also means customers don't have to worry about really things like capacity planning, orchestrating cluster rollouts, cluster scaling, administration, et cetera. And that's because everything is run as a serverless fashion. And compared to some of our other competitors in this space, this is a tremendous advantage. And the third reason is that you're protecting your investment for the next 5 to 10 years. And that's because of our modular architecture, we completely decouple the compute from the storage. And so when new compute engines become popular, so things like serverless Spark, notebooks, or analysis of unstructured data, you're able to associate this new compute functionality with existing data that you already have in your environment. So from storage to compute to networking, BigQuery is designed to bring all of Google's capabilities, all of our innovation and resources at the services of your queries. Now, at the end of the day, BigQuery Continuous Queries is just one of the building blocks of our data and AI portfolio. So while this feature allows you to run SQL queries in BigQuery in an unbounded fashion, it's the integration with Google's entire stack that makes this truly powerful and truly interesting. So from the ground up with our TPU and GPU infrastructure, which is purpose-built for machine learning, to our end-to-end machine learning platform with Vertex AI, Gemini, our model garden, machine learning APIs, et cetera. Getting up and running with powerful AI capabilities has never been easier and doesn't force data to live in disparate silos, and instead allows you to do more with your most valuable asset. And of course, with Google Cloud, you're adopting a platform, not a single tool, not a single API, not a single model. Google Cloud gives you the tools, the infrastructure, the capabilities to make AI-powered applications and enterprise-ready. So from the pre-built integrations to maximize AI democratization, productivity, and collaboration, to the built-in data governance, security, and privacy, to the immense scale that comes with building out infrastructure to solve Google scale problems, we've got you covered. And it's truly exciting to see that as companies have been adopting more and more of these capabilities, they are building things that are just truly astounding. It's really helping customers to reduce costs, decrease time to value, and build super, super exciting applications. And speaking of super exciting applications, I would like to welcome Pinaki Mitra on stage to talk about what he's been doing at UPS Capital.
My name is Pinaki Mitra. I work at UPS Capital, a subsidiary of UPS, and I have responsibilities for data engineering, data science, and analytics for the organization. UPS Capital primarily provides transactional package and cargo insurance to cover customer goods against loss and damage, including port piracy. So UPS picks up millions of packages a day, right? And then we have millions of customers, and then also there are millions of recipients of the packages as well. And then we have all these package movements data and package lifecycle data that creates millions of data points for us. And also from UPS Capital, we have all this insurance information and also the claims information for the customers. And then from the infrastructure perspective, we are completely using Google Cloud as a backend to store, process, model data, and drive insights. So using this massive data and Google infrastructure, one of the products that we have developed is Delivery Defense Shipping Intelligence. It provides an address confidence score for all US addresses where UPS has delivered any package. Our customer can access address confidence score either via an API or a web-based solution. An address confidence score, the API can be implemented at any point of journey of our customer's shipping journey. And then what we have seen through the data that our customers can avoid 40% of the losses using Delivery Defense Address Confidence Score. So how did we do it? So we are bringing data from various source systems and mostly from BigQuery projects. And then also there are other source systems where we're streaming data to our projects. And then a significant part of our work is the data sanitization, implementing business rules, and prepare the data for modeling. Since we're dealing with a lot of operational data, so there are a lot of data cleanup that needed to happen. And all this data wrangling work is getting done in BigQuery. And then once the data is ready, our ML models running on Vertex AI uses package, address, and loss features and generate the address confidence score. And an interesting fact is that we observed that about 2% of the US addresses that generate about 35% of the losses in that overall populations. So this address confidence score that we derived, it's actually designed in the range of 100 to 1,000, like a credit scoring system that we are all familiar with, and 100 being the worst and 1,000 being the best score. For the addresses with low score, there are ship to access point APIs that's available to our customer. And then customer can use that API to ship it to UPS access points. There are like about 20,000 and over access points available in US. And then the recipients of the packages can come and pick up the package from that access point. So we are currently using schedule queries to pull data multiple times a day for this project. Now, schedule queries are great, right? Simple to use, but still it's a batch processing and don't provide the real-time data as Nick mentioned earlier in his presentation. So I'm really excited that we'll have access to continuous queries very soon to bring the new data to our project as it becomes available to us. Now, we are working on several other data products, and then to help our customer and having access to real-time data without changing our core engineering model, which will be really, really beneficial to us. So we'll be able to update the features quickly to our models. So instead of running this batch process, this continuous query is going to pull the data to our project as the new data becomes available, right? That will help us to move these features very quickly to our models. And it will also help us identifying anomalies faster in our claims processing system to help our customers. For insurance solutions, identifying risk and anomalies early, it's really benefit our customer and also it benefit us. So now I'm going to hand it over to Pavan for a demo.
Thank you, Pinaki. Good afternoon, everyone. My name is Pavan Edara. I am a software engineer on the BigQuery team. So far, you've heard about a number of scenarios in which continuous queries can be used. For the next 15 minutes, I'll walk you through a few real-world applications to ground the material that you've heard so far around the possibilities with continuous queries. Before getting started, so how do you run a continuous query? We want to bring the simplicity of running SQL-based analytics, the familiarity of SQL, through the familiar BigQuery interface. So we try to make it really simple. So you write a standard SQL query, much the same way you write an interactive or batch query. In the BigQuery API, we introduce a new option to run a query continuously. You turn that on, and you submit the job. The job then runs continuously, indefinitely, until you stop it. So it looks for new data arriving in the inputs described in the query, performs the processing described, and writes the output to any output destinations. You can do downstream stream processing on that, or you can do downstream batch analytics on that same data that we output. So in order to run a continuous query, you'll need one more thing. You'll need a BigQuery reservation with the assignment type called continuous. Essentially, this tells BigQuery that some number of slots must be prioritized for continuous queries, because in order to run these queries in real time, you need some guaranteed resources. Our first application that we'll talk about is representative of a scenario of performing real-time follow-ups and real-time recommendations. So in this application, we have a retailer here who's tracking abandoned shopping carts. Essentially, what we are trying to do is the retailer would like to follow up on abandoned shopping carts in real time. The understanding is that real-time follow-ups are up to 2 times more effective than follow-ups that happen 30 minutes to an hour later. So essentially, what we have here is we have the abandoned shopping cart events table, which is essentially the abandoned shopping carts are flowing into this table. We put a continuous query on to process it. The continuous query combines the abandoned shopping cart events with recommendations from Gemini, outputs the data to a PubSub topic. We'll put an application integration workflow on top of this PubSub topic to listen to notifications from PubSub and send emails to our customers in real time. Let's switch to the demo. So shown here is the schema of our abandoned shopping carts table. It is pretty simple. Just for simplicity of exposition, we have taken a very simple schema. So we have 4 columns here, the customer name, the customer email, the last updated timestamp is the timestamp at which this event entered the BigQuery table, and the products column is a list of products in that cart. So we have our continuous query here. What we are doing is, let's get this continuous query started. What this continuous query is doing is, it's reading from the abandoned shopping cart table. It's listening to new rows in this table. It's constructing a prompt for Gemini. It's taking the response from Gemini, post-processing it, and writing the output to a pub subtopic. With the introduction of continuous queries, we are adding the ability to output to PubSub from BigQuery. So this query is running, and initially to start with, our abandoned shopping carts table has no rows. So this query really has nothing much to do. It will get started and wait for the new data to arrive in the abandoned shopping carts table. So in order to actuate this query and make it really do something, we'll add some rows to the abandoned shopping carts table. We'll do that via our real-time streaming API. So here we are inserting a single row, the JSON for which is shown here, the customer name, customer email, and it has a few products in their cart. We've inserted that row into the BigQuery table. Let's go back and check that this row has indeed made it to the table. There's one row in the table. You'll now see that this continuous query will process this data and write it to the pub subtopic. It will essentially call out to Gemini. It will use this generate text function to call out to Gemini and post-process the output and write the email content out to PubSub. As you can see here, it has read one record and written one record out to PubSub. Now, let's see if our shopper has actually got the email. Sometimes it takes a little bit of time. Yes. So as you can see here, the application integration workflow has picked up the message from PubSub. It contains recommendations for other items this customer can buy based on the items in their cart, and it's encouraging the customer to finish their purchase. This is an example of an application where real-time recommendations can be generated through a continuous query. Switching back to the slides for the second demo. Our second application is a little more interesting. We have, in the previous one, we had a single input source, which was the abandoned shopping carts table. Here we have two. We have a raw error log table into which many applications are collecting error logs through real-time streaming APIs. These error logs happen to be in different languages. Alongside this raw error logs table, we have a known issues table, which is a continuously changing list of known issues. This must be familiar to people who have used monitoring and alerting applications. How often have you seen real errors being missed out because there is so much noise in the logs? So the goal of this application is to filter out the known issues from the error logs and only write out any new errors that have been seen to this output table. In order to do that, we'll put a continuous query on top of these two tables, and we'll do a join between the two, between the raw error log table and the known issues table. We'll take the output of that join. I'll describe the join in a little bit, what exactly this join does. We'll take the output of the join. We'll feed it to a language translation model hosted in Vertex. We'll write the translated logs to a BigQuery output table. You can imagine writing these translated error logs to a pub subtopic, just like in the previous example, for further downstream processing. Let's switch back to the demo. Thank you. So the raw error log table the schema for the raw error log table is shown here. It has a number of columns, the timestamp and so on, the error message and the error code. The error code is the join column, as we'll describe in a little bit. The known issues table, so the raw error log table, actually we pre-populated with 2 rows. It has 2 rows, one with error code 002 and another with error code 003. The known issues table also has two rows, error code 002 and error code 004. The translated error log table is essentially empty at the beginning. It has no rows. So what we will do is, so here is the continuous query. As I described earlier, the continuous query tries to perform a join between the raw error log table and the known issues table on the error code field. In this case, given that we don't want rows that exist in the known issues table, we perform what is called a left anti-join between the raw error log table and the known issues table. We'll take the output of that join, essentially the rows that survive the filter, the anti-join. We run it through a cloud translation model. We output the rows, we process the rows, and our desire is to output these rows to a BigQuery table. I've pre-configured that. Let me show you. So I have set the destination table to a BigQuery table, and I have turned the continuous query mode on. So now let me start this. Initially, the initial contents of the raw error log table will be processed by the continuous query when it starts up. As described earlier, there are 2 rows, error code 002 and 003, and the known issues table has 002 and 004. So the net new errors that are seen that are not known prior is the error message with error code 003. What we expect to see in the translated error log table is that particular error code. Error code 003, as you can see, is now showing here in the output table, and it has also been translated prior to being written to this table. Let's make this a little more interesting. We process the initial data in the raw error log table, but now let's insert a few more rows into this raw error log table, essentially simulating applications writing rows into this table. So we have three error codes here, one row with error code 004, another with error code null, and the third one with error code 007. You'll notice that error code 004 is already present in the known issues table. So our expectation would be that once these rows are inserted, error code null and the last 2 rows should show up in the translated error log table. The continuous query detects the new rows that are inserted. It automatically runs the processing that is specified, does the translation, and writes the output. The query is always running, so there is there is no management of the query that needs to happen. The output is readily available anytime an application wants to consume it. As expected, we see error code 007 and error code null in the output, and also the error logs have been translated. So this is an example of an application that wants to perform continuous data enrichment of data coming in real time. This is very common in data warehouse applications where you have fact tables and you want to the data coming into fact tables is enriched with data in dimension table at the time of writing to the data warehouse. So back to the slides, please. Okay, so far we have seen 2 applications with different functionality, one performing real-time recommendations and one performing joins. So to showcase everything that we do in BigQuery is big. We pride on our scalability. So we'll showcase the scalability of continuous queries a little bit. And since it's hard to showcase the scalability in a short, we have pre-started a query here. The application here is a real-time flight monitoring application. We have real-time flight events corresponding to their takeoffs and landings being recorded in a BigQuery table. We have a continuous query that is operating on top of it. It is detecting new flight events in this table, processing them, and writing the output to Bigtable. This is representative of a fast emerging class of applications that perform what is called reverse ETL. Compute in data warehouses operates on massive amounts of data. There is richly curated data in data warehouses. There are applications that want to use the richly curated data, massive amounts of it, and make it available for low latency real-time serving, online serving. So for that purpose, this application is using Bigtable for that online serving. Switching back to the demo, please. We have a flight record data table here. It has a number of columns. This is our input data table. We already have a background data flow job that is writing to this table at a few hundred megabytes per second. We wanted to showcase the scale, so we have something, an application writing to it already. So there are a few interesting fields. The most interesting field is the flight number. We will use this as the row key into the output Bigtable that I mentioned earlier. Shown here is so currently the flight record data table has been running for the last hour or so, and it has 72 gigabytes of data and 14 million rows. So shown here is the continuous query. We pre-started it. The continuous query is reading from our flight record data table in real time. It's processing the data in the table, constructing a mutation into Bigtable, and writing the output to Bigtable. As part of the launch of continuous queries, we are also introducing the ability to write through streaming through a continuous query into Bigtable. So it is writing into this Bigtable. We pre-created this Bigtable, and I'm going to show you the Bigtable monitoring dashboard to show that we are indeed operating at scale. As you can see, we are writing somewhere between 150 and 200 megabytes per second to this table. I want to point out that the scalability of this application is limited only, as far as we can think, to the amount of slots available in your BigQuery reservation and the amount of capacity available in your Bigtable instance. Beyond that, it grows, it scales pretty linearly with the amount of data in your table. So in order to demonstrate that this application actually reacts in real time, we'll take a unique flight ID, flight 999, and we will look for this flight in the Bigtable. So currently, there are no rows for this flight in Bigtable. Now, what I'm going to do is I'm going to insert a flight event into this Bigtable. I'm going to insert a single row into the BigQuery table containing the flight events, simulating a flight taking off from Seattle, and which is en route to Maui, and its status is in flight. The continuous query will observe this row, will see this new row in the BigQuery table, perform the processing, construct a mutation into Bigtable, and output the mutation to Bigtable. So in order to do that, we'll go to the Bigtable Studio again, where we were looking up for this key, and we'll look up for this key one more time. As you can see, the flight 999, the row corresponding to flight 999 is now visible in Bigtable, and its status is in flight. Let's take this one more step forward. Now, at some point, this flight will land in Maui. Let's insert a row to record that landing. So the flight, it is the same flight, flight 999. It took off from SeaTac, and it was en route to Maui, and it has now, we have marked its status as arrived. Again, the continuous query will notice the presence of this new row in the BigQuery table, construct a mutation, and upsert the previously written row with the same row key into Bigtable. The flight number was the same one, flight 999. It's flight 999 that we marked as in flight, and flight 999 that we marked as arrived. So now we go back to the Bigtable UI, and we look for that flight. And as you can see, this flight has now landed. Any application that wants to serve this flight status, let's say on your mobile app, can read this data and serve the status of this flight. We think of continuous queries as also a vehicle to transfer data between systems. Think of the number of pipelines that you would have to write in order to move data from a BigQuery table into Bigtable. Our goal is to make it easy with a single query for you to run this in a way that BigQuery manages it entirely end-to-end.
Yeah, so we are happy to stay a little bit longer and take some more further questions over to the sides in order to let the next speakers come up and get prepared and all that. But thank you so much for joining our session.
Thank you.
We're super excited about this capability.